Welcome to another episode of Dominic Does DIY. As always, like, subscribe, hit the bell, comment down below if you find this entertaining or useful. Also, if there's something you'd like to see or explain, let me know in the comments down below. And now let's get on with the design. Today we will be looking at half an H bridge designed to be controlled by a standard 5-volt signal input. Usually we pair up two half bridge systems to make an H bridge to control a motor or advanced buck boost circuitry. So the design shown is a full H bridge, but I just locked the right side to have the high side FET on and the low side FET off. This basically means we pulse the gates on the left side. We should see current flowing directly related to the input signal. I put a resistor as the load there just to limit the current to around 50 milliamps or so. We know our system should work. I got PMOS on the high side and NMOS on the low side. The VCC supply on the top is 5 volts, and the gate pulse voltage is 5 volts. So we will be able to control the PMOS and the NMOS with the 5 volt pulse. Normally this 5 volt pulse comes from a micro to control the system. Of course, I'm simulating that with a DC pulse supply, but the effect will still be the same. I'm going to pulse the system at 20 kilohertz, pretending we are trying to PWM a motor or something. Quick analysis of the system, since M2 here is held on, and M4 is off. When we turn M3 on, we will have current flow, and when we turn M3 off, we won't. Normally in a fully functional H bridge, this would be considered forward motion. And when we would turn M3 off, we would turn M1 on and M4 on in order to run the motor in reverse. So let's go ahead and run this and see the current through R1. So just as we expect, we can see the 50 milliamps coming through the system right here through R1. And we can see that it's directly related to the pulse. So as our pulse goes high, it turns on M3 because M2 here is locked on. Then we get current flowing through R1 like that. So it's just like we expect. Whenever the signal goes high, M3 turns on and we have current flow. When the signal goes low, M3 gets turned off and we lose current flow. However, let's take a deeper look. So we know the current through R1 is looking good, but let's not look at R1. Instead, we're going to look through the current through M3, right? Let's look at the current going through the FET. So you can see the current going through the FET here, we have a slight problem. Our current is no longer 50 milliamps. You can see our scale over here. It's going all the way up to 180 amps. So it looks whenever the signal goes from high to low, we get about a 20 amp pulse of current going through M3. And whenever the signal goes from 0 to 5, we end up getting almost 180 amps, maybe like 170 amps pulse going through M3. What this is called is shoot through. And why this happens is because of the internal resistance and capacitance that's naturally found in FETs. You can find this on the data sheet as like CISS, and it talks about the internal gate resistance that comes on there. Usually these are really small. We're talking picofarads and like less than 10 ohms on the gate resistance. But that RC time constant causes the time on delay, plus all the electrons and stuff. So you look at the data sheets and they have time on delays, time off delays, and that's what's causing this shoot through. So what's basically happening is when we go from 0 to 5 volts, right, when it is 0, M3 here is off and the PMOS is on. And when we go to 5 volts, right, what's happening is the NMOS is turning on before the PMOS can turn off. And because of that, we end up with a high current pulse coming from VCC through M1 through M3 to ground. And because the RDS-ons of these are very low, then we get a very high current pulse that comes through, which we can see right here. This is a pretty common issue in the world of motor controls. And really, you don't ever have to solve this. Usually you will be using a motor driver IC or something that has shoot through prevention by independently controlling the gates and having time displacement between the turning on and the turning off of the FETs. Or worst case is you're controlling these things directly. So right now we're saying that we have one pin available on the micro and that one pin's got to control both FETs at the same time. But usually we have a micro that has multiple pins. And so we could solve this too just by saying, well, the micro will control independently this gate with one pin and this gate with another pin, and we can prevent this shoot through with some time displacement, just like the ICs do. However, that's not what we have here. We have a single signal, and we need to add some hardware to chop down that 170 amp pulse to get that down, because that 170 pulse will actually take out one of these FETs. So you need to fix this in hardware so that we do not have the shoot through. In order to do this, you just have some resistors, some capacitors, some diodes. You can use whatever value, whatever diode you want. So resistors, caps, diodes, that's all you're allowed to use for this exercise. So pause the video now if you'd like to solve the problem. So the first thing we have to ensure is that all the FETs are off before we switch the other FET. So we need to make sure that when M3 is on and M1 is off, we want to make sure that M3 turns off before we turn M1 on, and vice versa. When M1 is on and M3 is off, before we switch over, we want to make sure that M1 shuts off before M3 turns on, and that'll prevent the shoot through. So how can we do this? Very simple. Let's just work in one idea first off, which is the 0. Let's say we're starting at 0 volts and we're going to 5 volts. Well, if we're at 0 volts, then that means that M3 is on and M3 is off and M1 is on. And so when we go from 0 to 5, when we transition from 0 to 5, when we go to 5 volts, that's going to turn M1 off and M3 on. But we want M3 to turn on after M1 turns off. And the easiest way we can do that is with a simple RC time constant, right? So if we just go and put RC time constant to the gate of that NMOS, now when we go from 0 volts, and that's on and that is off, well, when we go to 5 volts, before M5 can turn on, it's going to go through this RC time constant here. So there's going to be a little delay in turning M5 on, and now M7 will turn off before M5 turns on. So let's take a look at that. We don't want to look at M3 anymore. We want to look at M5. Current through M5, the signal is the same. So you can see here with our signal, we did in fact take care of the 0 to 5 transition. You can see right here, there's no pulse here, right? We have no shoot through right here. But what's happening now is we still have some shoot through happening for 33 amps. We have shoot through happening in the transition from 5 volts to 0 volts. So when it's 5 volts, the M5 is on, PMOS is off, the high side FET is off. And so when we go to 0 volts, this high side is turning on long before this low side FET can turn off, because now we've got to dissipate this cap through another RC time constant right here for the discharge aspect. So you can see that's what's happening here. We get the shoot through as the RC constant is discharging until that FET turns off. So one thing that we can do, right, is when we're going from the 5 volts to the 0 volts, right, now we don't want this RC time constant anymore, right? We want to basically bypass this RC time constant so that our NMOS can turn off fast, right? Because that's the ultimate thing, is we want this guy to turn off before this guy turns on. And so we want to get rid of this RC time constant. The easiest way we can do that is by bypassing it with a diode. Right, so if we come here, we can see, so I've got my RC time constant when I'm turning on. It's going to use the RC time constant. But when I go into the off mode, when this becomes 0, well, now my current will flow through D1 instead of going through this time constant. Through the resistor, it'll just go through D1. And so that should expedite my turning off of that low side FET. So remember, we had this pretty long delay right here, like maybe what, like 5, 10 no, maybe not, maybe like 5 microseconds of shoot through going on. But now we've got the diode right there. So let me just delete this trace. And then if we see the current going through this one, we can see I've still got the shoot through. It's just a lot less, right? Because now I'm able to bypass this RC time constant, but I've still got the shoot through. Because now we basically still had the same problem from step 1. Remember how we had, it was really zoomed out, and I was like, it's about 20 amps of shoot through during this transition, and we had 180 amps of shoot through in the 0 to 5 transition. So we're still seeing that because I basically now just went back to step 1 where both of the wires are shorted. So how can we do this? Well, if we look at this circuit here, we can then go ahead and do the same thing, right? When I'm going from 5 volts to 0 volts, I want to do the same thing. I want to just add this RC time constant to delay the high side FET from turning on until after this one turns off, right? So I'm going to go ahead and add an RC time constant right here, like this. And so now when I go into the off mode, now I've got this capacitor charged, right? Because I've got 5 volts. So this guy's on, that capacitor is charged. So when I go to 0 volts, right, now the low side FET will turn off immediately because it's going through this diode. But the PMOS, it will not turn on immediately because it's got to discharge this capacitor through this resistor to ground. So I'll have a little RC time constant and delay it turning on. And so the low side FET should turn off before the high side FET turns on. So if I look now at M17 and the current, so you can see it is still getting some weird shoot through going through here. It's because now we've got the shoot through going through. We basically stopped the shoot through here, right, on the 5 to 0 volt one, but we've returned the shoot through back from the 0 to 5 volt transition, right? Because now in this circumstance, when we're going from 0 to 5 volts, we've just went back to square one, step 1, right? Because they're both going through this RC time constant, and so there's no delay. So I need to be able to, in the 0 to 5 transition, I need to be able to short circuit over this RC time constant so that I can turn this guy off before this guy turns on, just like we put the diode there so that this guy could turn off before this guy turns on. Same thing, we're going to want to put a diode here to bypass this RC time constant so that we can turn this guy off before we turn that guy on. So if we look here, we've got an RC time constant and we've got diodes going in opposite directions in order to facilitate the fast turn off of the FET. And we have the RC time constant to add the long delay to the turn on. And so now if I measure this current, you can see here, we've got just a minimal amount of shoot through right here, just a little bit, insignificant really, right? Because we're still sitting at 50 milliamps as our baseline square wave. The only thing that you will see here, so you see here, we have this little delay, this 3 microsecond delay right here of when the signal goes from 0 to 5 volts. We have this delay because of this RC time constant of turning on. So we turn off immediately. You can see here when the signal goes low, we turn off immediately. There is no delay because we're going through that diode to turn it off. But to turn it on, we're going through this RC time constant. So that's where that delay right there is coming from. But other than that, it is a pretty solid square wave that we have going on. That's all I have this time. Thanks for watching, and I hope you enjoyed the video. And thanks to all who have subscribed and shared. And I will see you next time.